Evening. As you all know, I hope I'm going to talk a little bit about how wings work. More precisely, I'm going to talk about lift and how it is generated, or what it is that causes lift in wings. And the reason I'm doing this and why I'm quite keen to do it is because it's been an old gripe of mine that it's often explained wrongly. And I think it doesn't need to be explained wrongly. You can explain it the right way without making it too complicated. And that's what I will try to do today. Just to a little reminder, it so happens that I've just written a little article about that very thing, which has just come out in the Journal of Physics Education. And there is a website, and I think, I won't guarantee it, but I think that if you go onto this, you can download the article free of charge. But don't blame me if you can't. So if you thought that today's lecture was any good, then you might want to download it. If you thought it wasn't very good, then just forget about it. I'll put this on here for those of you that want to quickly write this down. Right, now, I'm sure that all of you are aware that right now is a pretty good time to think about lift, because almost exactly in 2 weeks will be the 100th anniversary of the first powered flight by the Wright Brothers. So I don't know if this was a coincidence or not. In fact, I think it was a coincidence because I only had time today. So, but I think it's quite nice that I should be doing this 100 years after, so there is at least some topicality. Okay, with that, let's see what I will talk about today, give you some idea. As I've already indicated, there is an explanation for lift, which I call the popular explanation. It's one that I suspect some of you will have heard already, and we'll check later to see how many. It is an explanation that is unfortunately very widely spread. You can even find it in some books. And to my knowledge, the Royal Air Force even teaches it, certainly to its air cadets. But one of my good friends is a Tornado fighter pilot, and he's been given the same explanation for lift. And I'm claiming that it's completely wrong. And I'll tell you all why it's completely wrong. So next time somebody tries to sell you this, you have some pretty convincing arguments to make them struggle a little bit. And then we're going to talk about what is right. And before we do that, I'm going to talk a little bit about what assumptions and simplifications we have to make if we want to understand the flow of air over objects in a very easy way. I will then talk a little bit about Bernoulli's equation. Again, something you've probably all heard before, but probably not something you're completely certain about, or you're not too happy about how it all works. I think that Bernoulli's equation is actually quite an easy concept once you realize where it comes from, and I'll try and demonstrate that today. And then we will talk about, this is the crux here, flow along curved streamlines. I will try and talk a little bit about what goes on when flow is not straight but curves around objects, because this is where I think the secret of lift is buried in there. And then I will finally come to the whole point of this evening, which is to give you an alternative explanation for lift. And from moving on from that, we can make a few other interesting observations about wings and other objects. Okay. So first of all, I've already forgotten that I was going to show you something. In order to explain to you what anything about lift, or how the popular explanation for lift works, I've brought along a wind tunnel. And it's this device here, which looks a little bit shoddy, but trust me, it's one of my favorite machines. I'll switch it on in a minute. What will happen is we will have flow coming from the bottom upwards, and I will put smoke into the flow. So if you can smell something funny, something burning, it's completely deliberate, and it's the smoke here, and Jane Blunt need not come and arrest me, at least not quite yet. We have, just to be on the safe side, switched the smoke alarm off in here. I'm waffling because I forgot to switch it on, and it takes a while to heat up. So this is not my amazing lecture technique. We're getting there. Right, what will happen is I'll turn this on. So I'll get some flow. I've obviously got an aerofoil in here. And what I will try and do is demonstrate to you what the flow over an aerofoil looks like. And an aerofoil is, of course, the cross-section of a wing. And what we're trying to understand, it'll get better in a minute, what we'll try and understand today is how come that when we immerse a cross-section like this into a flow, that we get lift. Why is it that we manage to get lift? Okay, whoop. Right. And I'll turn it up a bit. Okay. Sorry, if I poke your eyes out, I apologize beforehand. Okay, here you have the cross-section, the aerofoil section. That is just the typical cross-section for a wing. You can see that the flow is from left to right. At the front is what we call the leading edge of the aerofoil, or the nose. At the back is the trailing edge. And what you can see here quite nicely is that the streamlines sort of try to follow the contour. We've got a slightly... I'll ease off a bit on angle of attack. Okay, now it's a bit better. And you can see quite nicely how the streamlines follow the shape of the wing. They're hugging the wing on both sides. I think that picture, this is really all I require you to believe, is that the flow looks like that. If you can live with that, then I'm sure you'll understand lift. Now, I'll switch this off now. The typical explanation for lift uses that picture by saying that we have an aerofoil in the flow, something like this. We have streamlines. This is our leading edge, if I call that point A. This is our trailing edge, point B. Then the way it goes is that they're saying, okay, there is a longer distance from A to B along the upper surface compared to if we travel along the lower surface. And because there is a larger distance on the upper surface, in order to reach the trailing edge at the same time, particles traveling along the upper surface have got to travel faster. And then people say, well, and if they have to travel faster, there is this wonderful principle called Bernoulli's principle, which states that when air moves fast, it has a low pressure. And in order to prove that, what people then often do, not always, but often, they say, okay, here's a piece of paper. If I blow on this, it rises. And they're saying, well, the reason why it rises is because I'm blowing over it, so I have fast-moving air on one side and not very fast-moving air on the other because it's still, so I have low pressure above, and that's why it rises up. And that is effectively what happens here. So they say air moves faster because of the longer distance. According to Bernoulli, faster-moving air has a lower pressure, and as a result, the pressure on this side is lower than on that, and bingo, we get lift. Now, if I were nasty, I would ask you all who's heard this explanation before, and I think I would like to know. So who's heard this explanation? Yes, okay, thank you very much. I won't ask whether any of the people who gave you that explanation are in the room. That would be really, really horrible of me. Now, I'll give you a few reasons now, a few arguments why this explanation is completely wrong. There were a number of mistakes in that explanation. First of all, something you may or may not have thought about. A sailboat. If you think of a sailboat, what does it do? Well, effectively it's got two sails. The wind comes sort of from one side, and the sail generates a force which goes into a direction which is different from the wind direction. And actually, if you look at it from above, and you think of the cross-section of a sail, then basically a sail is not very different from a wing. You can imagine that a sail, if this is your mast, the sail is curved. We've got wind coming in one direction, and what the sail does is it generates a force like this. And if this is your sailboat here, you'll see that, then you see that a component of that force is pointing in the forward direction. That is your thrust. That is why sailboats can propel themselves forwards. So a sail on a sailboat is nothing else but a wing, and it generates lift. And now you might already see why that causes us a problem if we believe in the explanation I've just given you, because now look at the distance. If we look at the streamlines here, streamline going on one side and a streamline going on the other, what's the difference in distance? Well, there isn't any. If we ignore the mast for now, then a sail is just a very, very thin sheet of fabric which is just as long on one side as it is on the other. And there is no such thing as the air on one side taking a shortcut and you having some sort of recirculating flow in here. That doesn't happen if you have your sail adjusted properly. And you can tell that by having little telltales on the inside, little wool tufts, which show you that the flow does indeed follow the sail on both directions. So clearly here you have a wing with the same distance on both sides, and yet it generates lift. It works pretty well. So that is the first thing that might worry you about this explanation of lift. Up. The next is another one of these that I sometimes got asked when people have heard about this explanation, and that is what I call the equal time argument. Going back to the picture, it was stated that if we have two streamlines, one along the lower surface and one along the upper surface, and the streamline pattern looks fine, we've just seen that. But it is now claimed that if you have a small fluid particle or a fluid element, say one here and one there, if they are next to each other at this point, and they now travel on the two sides and move along here, then it is claimed that they must meet up at the end at the same time. Well, why? If you have a friend and you walk around a building, one goes one way, the other goes the other, why should you meet up at the other end at the same time? There is no reason. You're probably, when you heard this explanation, you were probably wondering why should they meet up at the same time and thought you'd overlooked something. Well, the answer is you haven't. You haven't overlooked anything. There is absolutely no reason why those two particles should meet up at the same time. And I go back to my toy before I burn it out. And I'll try and demonstrate this to you. Okay, we have a nice fat bit of smoke. And what I will now do is I will pulse the smoke like this. So the smoke now enters at the bottom pretty much at the same time. What I want you to do, first of all, in real time, is see if you can tell whether the particles on the top or on the bottom reach the trailing edge sooner or later, or whether they reach it at the same time. I have no idea how clear that is. But I think you might suspect that when we reach the trailing edge, we don't have the same time. And just to prove it to you, I'll do the old cookery program trick. Here's one I prepared earlier. I'm not cheating, because if you did look very carefully at this thing before, you would have spotted it, but we have an even fancier smoke wind tunnel in the department. And I took this sequence of shots. Okay, well, yeah, okay, I did. Oh, here we are. Now watch the line of smoke. It's pretty much all aligned there. And now do you see how it's beginning to accelerate on the upper surface and it's slowing down on the lower surface? Now these particles are almost at the trailing edge. Here they haven't even reached halfway. Here we're now clearly beyond the trailing edge. On the lower surface we've just about reached halfway. And there's absolutely clear, I think without the shadow of a doubt, that particles traveling along the upper surface are reaching the trailing edge before those on the lower surface. And this is where we need to stop it before you get a preview of what's to come. Okay, so that's argument 2. And then finally, not really a flaw of this particular argument, but another little gripe that I have with this. You could see I'm a bit pedantic. This thing is not a demonstration of Bernoulli's equation. It is, of course, completely true that on one side we have fast-moving air and on the other side we have slow or not at all moving air. But that's not the reason why there is a force on this paper. And I can demonstrate that that's true by hanging the paper straight down and now blowing on one side. And nothing happens. If anything, it goes the other way. But as soon as I hold it like this, it very clearly gets sucked up. And that is really the secret of lift. So you're already getting a bit of a hint of what's about to come. So, how can we get it right? And in order to get it right, I have to make some simplifications, because fluid dynamics is obviously the topic that I do all my work in and that I really like a lot, but it is a bit complicated, which is great, so it keeps people like me in pay. But to make it a little bit easier, we have to make some assumptions, and this first assumption is that I treat the flow as incompressible. I know we're dealing with air, and we all know from our bicycle pump that air is extremely compressible. If we have time at the end, I'm happy to argue the case why we can get away with treating it as incompressible. But for now, you should just believe me that that's a good assumption to make. And also, you might have heard of hydrofoils. And hydrofoils are just aerofoils that work underwater. And they look very similar to aerofoils, and they produce lots of lift. So clearly, whether air or the fluid you're dealing with is compressible or incompressible has absolutely nothing to do with how lift is generated. And I hope you're reasonably satisfied with that. I just want to satisfy the few aerodynamicists that might be sitting here, and if I don't say I've treated it as incompressible flow, they might kill me after. The next assumption I will make is that the flow is steady. Now, again, that's one of those things that we like to take very serious, whether flow is steady or unsteady. For now, you've seen that when I had this picture on, the streamlines look pretty much the same regardless of time. So whether you looked at 1 second or 5 seconds later, the overall flow pattern was pretty much the same. And that's what we mean by steady flow. Unsteady flow would be like a flapping wing or a wing that you very rapidly rotate or anything like that. Would be unsteady flow, but what you've seen there and what most aircraft do in normal flight is reasonably steady flow. So that's a good assumption to make. What we will now do, and where my whole argument hinges, is on taking a small element of fluid, a small volume, an imaginary volume. So a little chunk of flow that moves through the air, and looking what forces act on that chunk of fluid. So I'm not talking about a small volume that's the size of a molecule. I'm talking about a sort of a small fluid element. So what we are interested in is the forces acting on a fluid element, which is a small imaginary bit of fluid. And so the first question we ask ourselves is what forces might be acting on this? Well, the first is the fairly obvious one, is gravity. But air is pretty light, and the sort of forces we're after are actually much bigger than gravity, so we're neglecting that, which is a good one. It's always good to neglect stuff. That's really quite nice. The next one is friction. Friction's a tricky one. Friction is quite important in airflows, but we also know that air doesn't have a lot of friction. If you do this in air, you hardly feel anything compared to when you do this in water, for example. And again, we're going to neglect friction. We're starting to run out of ideas now. What other forces could there possibly be? And is this Babinsky guy going to neglect that too? Well, there is one more force I'm interested in, and that's pressure forces. And those I will not neglect, because pressure forces are obviously important, because we've already seen that lift is likely to be from the balance of pressures acting on the surface of the aerofoil, and that's where our lift comes from, so clearly pressure forces matter. And right now this will all seem rather abstract to you. Now imagine a small fluid element, and just for sake of argument, imagine it looks like a cube. So this is a small imaginary cube of air that's happily traveling with the flow. So just keep that thought in your mind. And it has 6 sides, and that means on each side there is a pressure. So there's a pressure on this side, there's a pressure on this side, below, above, and here in the front, and then there's one in the back. And now when we deal with hydrostatic pressure, what we usually say is that all these pressures are the same. If all these pressures are the same on all 6 sides, then what net force do we have? Well, we have 0 net force. If the pressure on this side is the same as the pressure on that side, then we have no force in horizontal direction, and so on with all the other sides. So if the pressure is completely uniform, then we have no net force. But if the pressure varies, and I will come to that in a minute and explain what I mean by varying pressure, but if for some reason the pressure on the left is higher than the pressure on the right, then you can see we will end up having a net pressure force to the right. So if the pressure is not uniform, we might have forces on our imaginary fluid element. And what am I going to do with that force? All I'm going to do is I will look at the sum total of all the forces acting on a fluid element, and I will apply Newton's second law, which states that forces are equal to mass times acceleration. That's the only equation you're going to see. And I trust you've all seen Newton's second law. So, are there any other forces? No, because I've neglected them all. So, what this is all now hinging about is that I am going to look at a number of flow situations. And I'm going to see whether the pressures are the same on all sides of my imaginary fluid element or not. And if they are all the same, then we have no force, and as a result, we have no acceleration, which means the particle will move in a straight line at constant speed. However, if for any reason we have any pressure forces, because the pressure is not equal on all sides, then we must, according to Newton, and he tends to be right, then we must have an acceleration. And that's the whole secret of fluid dynamics. Okay, so let's look at a very simple case. Let's imagine we have a streamline, so a straight streamline, and we have a fluid particle. That wasn't very good. A fluid particle. Again, I go back to my cube because I'm kind of boring. So here we are, cube. And that cube is traveling along this streamline with some velocity v. And we're really, to make it even simpler, right now I'm just interested in the pressure on the back and on the front. So I'm interested in the pressure here and on the front there. Pressure, of course, always acts normal to the surface and always inwards. Right. Now, if this is in a uniform pressure, then the pressure in the front and the pressure in the back will be the same. And what do we learn? We learn immediately that the velocity of this fluid particle will not change. It will not accelerate, it will not decelerate. But what if we have a pressure variation? What do I mean by that? Well, let's say if we call that streamline S, and this is our coordinate S, if we look at pressure, let us say for sake of argument that we're in a pressure field where the pressure drops as we go along the streamline. Then because this particle has a finite size, I'm being very crude here, because it's not infinitely small. I said it's not the size of a molecule. It's a little bit bigger than that. So because it has a finite size, you see that the pressure on the back is higher than the pressure on the front. I hope that's reasonably clear. And if I can find a different pen, what that means now is that this pressure here is larger than that pressure there. And what do we learn? We learn that we have a net force which is forward to the right in your picture. This pressure is bigger than that, so we must have a net force to the right. And according to Newton, who I've kind of scrolled away, but there he is, F equals m times a. Because we now have a net force, we clearly must have an acceleration. And in which direction is the force? It's forwards. So the particle will accelerate. It will go faster. So we have pressure drops along streamline. That's this example here. There, so we see that the particle accelerates. Oops. My writing is a bit of a scroll, I apologize. And of course, if we have the opposite case, if the pressure increases, along streamline, then the particle will slow down. Now this is quite important, because if you understand that, then you've already understood Bernoulli's equation. There is not more to it than that. Because what are we saying now? If we are along a streamline where as you move in streamwise direction, the pressure drops, becomes smaller and smaller and smaller, then that means that there is always a net force on particles which accelerated, which means the further we go in this direction, the larger our flow speed will be. So what we're seeing is that there is a connection between the level of pressure and the flow speed. What I've really showed you is that there is a connection between pressure gradients and acceleration, but you can integrate that up, and it's easily done, but I won't do it now. And what will come out of it is that pressure and flow velocity are intimately connected. If the pressure drops in streamline direction, then the velocity will go up. And alternatively, if you have a streamline which is running into a domain of increased pressure, then the fluid particles must slow down as they travel along it. And, I promised there would only be one equation, but just for sake of argument, I really should show Bernoulli's equation. For those that don't know what I'm talking about, it states that P plus half rho V squared is a constant. Pressure plus, this is fluid density, we don't need to worry about that, but pressure plus velocity squared is a constant, which means that whenever the velocity increases, the pressure must decrease, and vice versa. And I can demonstrate that to you. Sorry. Here is a very, very simple experiment with a hairdryer. We've got a channel here which has a decrease in cross-section and then an increase again. And just from the old example when you put your finger over the hose pipe, that where the area decreases, the flow velocity must go up. I hope that's reasonably clear. So when you look at this, you will know that we have the highest flow velocity in here, and we have a low flow velocity there and there. For those that can't see it now, you can look at it after the lecture. And down here we have a manometer. This is just some water with some dye in it, and if I turn the hairdryer on, what we can see is that where we have the narrowest cross-section, the manometer goes up, which means that the air pressure here is much lower than it is before and after. I can't even go one faster. And you clearly see that where we have a high flow velocity, we have a low pressure, and where we have a low flow velocity, we have a high pressure. And that is Bernoulli's equation. So I've just proved Bernoulli's equation, so what am I so concerned about this example I've given you before? Well, there is one big but here. When I derived this thing just now, or I tried to, I derived it along a streamline. Strictly speaking, and this is often overlooked, Bernoulli's equation is only valid along a streamline. And if you're blowing over a piece of paper, or if you took a hairdryer and blew over it, I say hairdryer because I can sketch hairdryers easier than I can people. Then what you have is you have streamlines coming out of the hairdryer. Here's your piece of paper. And they go along here like this. And then down here, well, the air doesn't even move, so strictly speaking, there aren't even any streamlines. But even if they were, the Bernoulli's equation, P plus half rho V squared, is a constant. If I call that constant C1 here, then for the streamlines down there, P plus half rho V squared, that is a constant C2. And what is very, very important is that in general, C1 and C2 are completely different. There is absolutely nothing in Bernoulli's equation that states that those two must be the same. There is no such thing as a Bernoulli's constant, which you can look up in a textbook. All Bernoulli's equation says, it says that along a streamline, this is a constant, but it doesn't say what that constant is, because it depends on what the streamline is. And because these streamlines come from a hairdryer, they have a higher energy, because that's what the hairdryer did. It pumped energy into the flow. And that means that this C1 is much larger than C2. And that is the problem with using that to demonstrate Bernoulli's equation, because you are not comparing apples with apples. You're comparing apples with pears. You cannot compare the streamline below with the streamline above, because you cannot apply the same Bernoulli's constant to both of them. And you can see immediately that you're going wrong by blowing over the straight piece of paper when the thing doesn't move. And now you know the reason why, because Bernoulli's equation is only valid along a streamline. Sometimes a number of streamlines come from a common reservoir, like in this hairdryer, and then you might suspect that all these streamlines have the same value of Bernoulli's constant, and you wouldn't be too far wrong. So sometimes you can get away with it. But strictly speaking, you can't, because you must only use Bernoulli's equation along a streamline. Okay. Now we come to the more interesting case. I've just talked about flow along a straight line. Now what happens if we have a streamline that's curved? So if we imagine a streamline that is curved, like this, say it has a radius of curvature, capital R, and now again we look at a fluid particle, and let us now, just for sake of argument, it's actually not important, but just to prove that you've just learned something, or I hope you have, if that particle travels at a velocity v, and if that velocity v is constant along the streamline, then what can you immediately conclude about the pressure along the streamline? That it's constant. The streamline may be curved, but the pressure at one end here, the pressure there is the same as the pressure there, because the velocity of that particle is constant along the streamline. And that's Bernoulli's equation. So great, we've already learned something. But I want to come back to Newton. Force is mass times acceleration. And if anything moves along a curved path, then one thing you will have all learned is that there must be something giving you a centripetal force, because there is an acceleration inwards. Otherwise, if there weren't such a force, what we need is a force that goes downwards. If it doesn't exist, the particle will go along a straight line. You must have something that gives you a force downwards. And where does that something come from? Magic? No. We've neglected all forces except for one, and that one thing that we have not neglected is pressure. And now we look at the pressure on one side, up here. If I call that P outside, if you don't mind, because it's on the outside of our curve, and the pressure on the bottom, and I call that P inside, then my argument is, and that's what all this revolves about, is that if this particle is moving along a curved path, then the pressure on the outside must be greater than the pressure on the inside. So P outside is greater than P inside. Now this I'd like to sink in a bit, because this is really very important. Just as important as Bernoulli's equation, actually, when you put it down in mathematics. What this now says is that whenever you see a streamline that is not straight, whenever you see a streamline that is curved, then there is a pressure difference between the two sides, or more correctly, there is a pressure gradient across the streamline directions. In this case, a pressure gradient in this direction. And the pressure is always larger on the outside. And I'll give you an example for that. Imagine a vortex, or if you like films, you might prefer to imagine a hurricane or something. What do the streamlines look like? Well, they're all sort of concentric circles, looking from above. Now pick any of those, say this one there. What I've just tried to explain to you is that this streamline is curved because there is a higher pressure on the outside than on the inside. The pressure drops as we go from here to there. And then what happens? There is another streamline which is equally curved, so the pressure has got to drop again So it's even lower here. So there, the pressure is lower than here. Do this like this. The pressure, if we go here, is higher than the pressure there. But that pressure is higher still than the pressure there. And that pressure is higher still than the pressure there, and so on. So what you can see immediately is that here in the middle, we have a very low pressure indeed. And if you ever wondered why, when you watch Twister or something, you see cows flying through the air, they get sucked up because there is a low pressure. And that's exactly what it is. It's lots of curved streamlines. You can see the same in your bathtub vortex. So if you have many curved streamlines, you can see that you can get very low pressures on the inside. And I've got another example for you, one that you can try at home, and is reasonably safe. Imagine you've all got taps, so next time you go home, you turn the tap on, and you get a nice stream of water that comes straight down, like this. I will simulate this with that beaker of water. You might want to sit somewhere else for a moment. I'm not very good at this. If you don't mind getting a bit wet, then what I will do is I will take this, and put it in the stream. Something like that. Okay. And so the water will fall onto this, and it will flow around the side. So we'll have something like that. And now the big question is, what happens at this point here, if I call that point A? Common sense, which is normally a very powerful tool, common sense would tell us that the water will then drop straight down. But let's have a look at this region here in a little bit more detail. If I try and blow that up, not literally, obviously, what we have here is we have these streamlines hugging the contour of my beaker. Say this is the water film is, these pens are dying on me. The water film has got this thickness there. The pressure out here we know is atmospheric pressure, just standard air pressure in this room. But now, you see where I'm going, I hope. We're going across a curved streamline. That means the pressure on the inside here must be smaller than on the outside. As you keep going towards the surface, in this direction, at least mentally you go across in this direction, you see that we're constantly crossing streamlines that are curved. The pressure across the curved streamline has got to drop if you're moving towards the inside. So as we're moving across, the pressure drops and drops and drops and drops, and by the time we get to here, or our point A, we can say quite clearly, I hope without a shadow of a doubt, that the pressure at A must be smaller than atmospheric pressure. We have generated a low pressure field on the inside. And now you have a jet of water there with a low pressure on one side and atmospheric pressure on the other, so there is a force inwards. And what happens as a result of which, this thing follows until at some point it can't anymore. So instead of falling straight down, it follows the contour. Excuse me. And I'll try that. But as I said, the trick is that you should all try this at home or at school. Okay, it's more or less falling straight down. I already see disapproving looks from the back there. This being wet, I think, is evidence enough that the water shot off sideways and, in fact, quite a long way. It's, in fact, very surprising how far it follows the curvature of this thing. This is the reason why teapots dribble. If I try and pour water there, if I do it slowly, I'm really good. I like this. It's not my lecture theatre. What you see is that the water, if you do it slowly enough, even follows that very, very tight curvature here for the very same reason. This thing has got a name. It's called the Coanda Effect. And it gives you the reason why fluids tend to follow curved surfaces. And you've seen it here. And that is just, I've showed you this because it's another illustration of the effect of curved streamlines and the pressure difference across them. And now finally, after 45 minutes of me prattling on and boring you to death, I know, we can finally go back to lift. I've now done my homework, and what I want to show you is, I won't run this again just yet. Here are two stills. Let's take the bottom one. I'll put it up there. This is what the streamlines look like on a lifting aerofoil. You've all seen it. You've all believed it. So I don't need to explain why it looks like that. But this is what it looks like. Now I'll try and sketch this. We have our little aerofoil here. Looks something like that. And the streamlines, they come up a little bit before. Some go over the top surface. Some go over the bottom surface. And as we go away, they gradually get straighter and straighter. In this picture, they're straightening out very quickly because it was taken in a tunnel not dissimilar from this one, and the walls are straight, and the streamlines have to be straight. If this were in free flight, it would take a much longer time for the streamlines to straighten out, but I'm sure you'd all believe me that eventually they will. So this is what the streamlines look like. I'm sorry, it's a bit faint. Different pen. Let's see if that one's got more power on it. If you leave the caps off, they don't write so well. So not only am I ruining all their lecture theatre, I'm also doing all the pens. So here we are, a little bit more strongly. Right, and now we apply what we've learned to this flow field. And that's what it's all about. Where the streamline is straight, a long way away, very high above the wing of an aircraft, or reasonably high, not thousands of meters, but a little high enough so that the flow is straight again. What do we know about the pressure? Well, we know that somewhere there, the pressure will be atmospheric pressure. Below our wing, again, reasonably far away, so that the streamlines are straight, we would also say it's probably atmospheric pressure. As I said, I'm ignoring gravity, so I'm ignoring any pressure gradients due to hydrostatic pressure variation for those of you that are worrying about this. We can ignore those, okay? We're talking about meters, not kilometers. And now, we mentally go from here along a path where we continuously cross streamlines. At first, the streamlines are straight, and we've already learned that if a streamline is straight, then the pressure on the two sides is the same. But as we get closer to the aerofoil, we start crossing streamlines that have a degree of curvature in them. And where are we relative to the curvature? We're on the outside, and we're gradually moving in. And because we've learned that whenever a streamline is curved, there is a higher pressure on the outside than on the inside, that means in the direction we're going, the pressure drops. So the pressure is lower here, and then we come across the next streamline which is curved, so it's lower still, lower still, lower still, lower still. And by the time we get to here, onto the upper surface of our aerofoil, we have a pressure, if I call that PUS, US for upper surface, we know that the pressure on the upper surface must be smaller than atmospheric pressure. And now we do the same on the lower surface. And again, we move up. At first, the streamlines are straight, so the pressure on both sides is the same. But then, gradually, we start noticing that they're a little bit curved. This time, we're moving from the inside to the outside of the sense of curvature. And that means we're moving from the low pressure to the high pressure, because the pressure is always high on the outside. So the pressure here is a little bit higher than there. Then we keep going across the next streamline, and the pressure is higher still. And so on until we reach the lower surface. And we've now seen that because we've crossed curved streamlines, the pressure on the lower surface must be larger than atmospheric pressure. And now we've proved that there must be lift, because if this pressure is larger than atmospheric and this one is lower than atmospheric, then we know, of course, immediately that our pressure on the lower surface is certainly larger than our pressure on the upper surface, and that is all we need for lift, a pressure difference between the two sides of the aerofoil. And that's where lift comes from. So if we look at that, what was it that has caused the lift? The thing that has caused the lift is the fact that we've put a shape into the flow which has introduced curvature into the streamlines. And the curvature is more or less the same on the two sides. And that introduction of curvature is what has given us the lift. And if you're still with me and you believe that, then I can show you a few other things. Here I have a picture. No, let's do this one first. What do shapes do to flow fields? Here I've got two pictures of a very thick and a very thin aerofoil. And you see that both of them distort the flow field. I've deliberately chosen two aerofoils that have a similar upper surface. And what you can see is that on both sides, the flow field curvature on the upper surface, oh, I should say, these are computer simulations using the exact equations of motion for an aerofoil. So they're not real, they're fake, of course, but they're pretty good fakes. Somebody's really tried here. So on both of these, you can see that on the upper surface, the curvature is pretty much the same. The flow field looks very similar above the wing, and that is because the upper surface is rather similar. So we would conclude that if we do this thing that I've just done, our marching downwards, that the pressure on this upper surface is clearly below atmospheric pressure, but it is comparable to that pressure. Now let's look at the lower surface, and the nice thin aerofoil here has also introduced some nice curvature, as we can see. Works really well. So clearly, if we do the same argument as I've just used, and we move from here all the way to the surface, we know the pressure must increase, and we should have a nice high pressure here. So we get a lot of lift out of this thing. Now let's look at this admittedly rather ugly and rather fat thing. Needs the Atkins diet or something like that. And what you can see here, that this curvature thing isn't quite as obvious anymore on the lower surface. In fact, we can see a little bit of the what I would call good curvature here. But down there, it curves the other way compared to this. So you might even conclude that we don't get a great deal, on the whole, we don't get a great deal of overpressure on the lower surface. And you would be right. In fact, we have regions back here where we even get a little bit of underpressure, pressure below atmospheric. So if I now ask you which of the two generates more lift, would you all know? I better not. I don't want to get too depressed in case I've really done a bad job. But I really hope that you're following me so far, and you would all conclude that this thing gives you much more lift because both sides are contributing to lift. You get a nice low pressure on this side, but also you get a nice high pressure on that side. Whereas here, the upper surface works equally hard as there, but the lower surface is a bit, oops, close run there. The lower surface doesn't do much. So this is better. If you think of birds, birds have very thin, curved wings. They have something like this. But aircraft don't. Why don't aircraft? Aircraft don't look as ugly as that, but they're certainly thicker than this. Why is that? Well, because you need structural strength. And if you try and build a jumbo with a wing cross section like this, I don't think you'd want to fly in it. And the other thing is you'd want to put your fuel somewhere, and you won't get a lot of fuel into here. But if we're talking about pure aerodynamic efficiency or the lift coefficient, then certainly this is preferable to that, which tells you that sails are actually pretty good wings. So that's just a little thought. Now, the other thing I want to show you is going back to the wing. A bit more smoke. Of course, this smoke is perfectly safe. You needn't worry. We're getting there. There'll be a bit more. So now you can look at this with new eyes. With fresh eyes, you can now look at the curvature. Isn't it brilliant? You see how the upper surface contributes more to lift than the lower surface in this particular case, which is true. And now what I will do is I will change the angle of attack. And I just want you to see what happens. If I make it less, oops, we get less curvature. No, hang on. What am I doing? Ah, sorry. I have to think. I can't hardly see what I'm doing. right? If I increase the angle of attack, we're already, what's happened now? Now we seem to have the same curvature on the two sides. This doesn't look too promising. We would worry a little bit about the lift here. And if you worried about this, you'd be right. I'll show you some nicer pictures of the same thing. Because what we've just seen is that normally, as you increase angle of attack from a small angle to a big one, you do indeed get more curvature into the flow, which means you get more lift. That's why when you come into land, well, no, let's not talk about that. It's got flaps and stuff. But there can come a point when suddenly, you see how this flow suddenly doesn't follow the surface anymore. That's what we call it separates. And in fact, in this case, if you guess that this doesn't produce a lot of lift, you'd be right. This is called a stall. And a stall is not a very good thing in aircraft. And just to convince you of that, here's another one I've prepared earlier. Okay, so there you see it on a better wind tunnel. You see how we get more curvature as we increase the angle of attack. Quite nice. More and more curvature now. The lower surface is working a bit, the upper surface is. But if we overdo it, and we'll soon get that bingo. See how very suddenly we lost the flow and suddenly we're not generating lift anymore. That's called stall. Up. Slightly over-enthusiastic here. Now this is what that looks like on a big aircraft. High angle of attack, lots of lift. Suddenly you lose all the lift. And whee! Now imagine that generally, that sort of thing enjoys happening when you're coming into land. So next time you're coming into land, just remember that thought. But as you've seen, aircraft manufacturers worry a great deal about stall. And they usually design the aircraft to get this right. And now finally, I have just one more thing to show you, and then I'm finished for today. I thought it's reasonably topical at the moment. I'll take the aerofoil out, and I'll put a cylinder into the flow. Is it still? I see I'm very close to overstaying my welcome, so bear with me for just one more moment while the smoke gets back. Okay. Now here we have the flow over the cylinder, and you can see it doesn't completely follow the curvature, but now what I will do is I will spin that cylinder, if I can find the switch. And now what happens, the cylinder spins clockwise, and you can see that the flow field that was symmetrical a minute ago suddenly is no longer symmetrical, and you can see that we have a lot more curvature up here than we have down there. And if you follow the argument logically through to its end, you would conclude that we have a low pressure region here compared to the pressure there. So there must be a force on this cylinder. It goes sideways. And that is exactly what people like Beckham do when they hit a free kick and they put spin on the ball. Watch it next time in slow motion. Watch the direction in which the ball spins, and you see that they generate side force. So David Beckham, when he lines up a free kick, he does a quick calculation of Bernoulli's equation. Maybe not. So before I burn my, one more, burn everything out, I'm coming to the end, and to summarize what I've tried to demonstrate today is that the distance argument that has been used so many times, that's it. that the old explanation for lift using the distance argument is completely wrong, and I hope you at least take that away today. Bernoulli's principle is no magic. It's actually something quite simple. It's really just Newton's second law applied to flow along a streamline. I happily derive you the full equation. It really only takes 3 minutes, but I thought you might not want to see too many equations. Curved streamlines also cause pressure changes, but instead of causing pressure changes along the streamline, that's what you use Bernoulli's equation for. Curved streamlines introduce pressure variations across the streamline, between the two sides of the streamline. And lift is caused by that very thing, by putting an object into the flow that introduces flow curvature. That is where lift comes from. And I'm happy to answer questions. Thanks very much.